5 or 6 parts since we have a lot to get through. Let me know if you can see my screen.
Yep, can see.
Okay, thanks. So today we'll kind of start with contrastive predictive coding, a couple of different versions of it. In fact, interestingly, while the first version was authored by Aaron Van den Noord, interestingly, the same guy who authored the Pixel CNN paper. It turns out that the second version of this, one of the co-authors was the guy or is the person who teaches this portion of the course, and it's a grad student at Berkeley. So one of the teaching instructors is a co-author on the version 2 of this paper. So where we stopped last week was kind of thinking of contrastive predictive coding as a generalized method that can be adopted for self-supervised learning and learning representations in multiple domains, like not just in one domain like images, but in multiple domains like speech, image, text, as well as RL. And the idea that underlying contrastive predictive coding is very similar, or you could say the concept is the same as that of word2vec. So in word2vec, for those of who are familiar with word2vec, what we tried, the word2vec paper authors tried to do is say that if we use surrounding words to predict the center word, or use the center word to predict the surrounding words, again, when I say predict, all this is in high dimensional embedding spaces for the words, then by doing this, that is by finding the correct words which are in the center of a group of words, and the embeddings that we learn are very useful to do a lot of downstream tasks, such as predicting sentiment, such as saying if the relationship between capital and the country, then we find similar distances between other capitals and of other countries. So things like this. So the embeddings, if we just follow this approach of putting embeddings which by some metric are deemed to be closer to each other versus farther away from each other, then by just doing this task repeatedly and optimizing, then we find that the embeddings that result are very useful for performing many things and seem to extract some information which are inherently present in the words. So that's kind of word2vec, and contrastive predictive coding takes that idea and applies it to a broad set of domains. And that's behind kind of the conceptual underlying principle behind contrastive predictive coding. And instead of using just the average of the words, for example, we say, hey, we have all these powerful neural networks, why don't we use them and use the loss? And remember, in word2vec, the loss that was being used is either because we want to make the probability or the loss of the correct word in one direction, optimize it, and all of the negative words, that is all of the words which are not the correct word for the center word, to have a much bigger loss. So the two methods they used to do this was either hierarchical softmax or contrastive, negative contrastive estimation loss. That is where the word contrastive comes from. That is, you contrast the correct answer with respect to all the negative answers, or the one positive answer with respect to all the negative answers. And that's where the contrastive part of the contrastive predictive coding comes in. So we first look at it in a speech context, and then kind of go from there to images, and very briefly to text and reinforcement, and kind of begin to look at where this approach leads us with in self-supervised learning compared to supervised learning. So let's say we take a audio waveform an audio signal, and based on a context audio signal, which is the past, we try to kind of predict the future audio signal, which we can kind of assume is X, and we try to predict the conditional value of X, that is the value of X in the future with respect to the context. But one of the things that we do differently in contrastive predictive coding is, instead of actually predicting the real audio signal per se, what we do is we encode the context with an encoder and do the same thing for the future audio signal. So take both of these into a latent space and then try to predict the future from X from the context, right? And we have kind of looked at in one of our previous lectures very quickly the concept of mutual information. So you can think of it as contrastive predictive coding as kind of trying to maximize, if you will, the mutual information between the context and the target. So the thing is we don't actually predict the sound waveform from the context. What we do is use an encoder, get the encoded representation. So it is of the context. So we have taken the raw audio waveform into a latent space, and we take the future audio waveform also into the latent space, and then we try to predict this Z in the latent space from the context by conceptually thinking of maximizing the mutual information between C and Z, right? So the goal, therefore, is for the encoder to learn representations of the underlying audio waveform such that this context is able to maximally be predictive of the actual future Z when contrasted with a lot of fake Zs, right? So that's kind of the setup. So what we want to do is encode a context and predict the target, but context and target are both in the latent space. And the way we do it is to say we maximize the predictive capability of C with respect to its ability to predict Z in the latent space. But how do we do that? We say for the correct Z, we want it to be maximally predictive of that. And the wrong Zs, we want it to be as far away, the embeddings that the encoder learns, we want it to be such that the correct Zs predicted by the encoding of C that we learned, and the wrong Zs are far away from the embeddings that we use to predict them. So that's kind of what you have going on in a CPC, right? So this is just basically the math behind it, and essentially it just says, by what I just explained, what we have done is, let's say there are a bunch of Zs, and if there is one positive Z, then we want the classifier to pick this positive Z and be able to classify it as the positive example, and all these negative Zs as the negative examples. And to the extent that the setup for CPC is able to do that successfully, then the representations that the encoder learns, if we now take out the encoder from this kind of a setup and use it to perform our downstream tasks, then we expect the representations that are learned by the encoder to be able to do downstream tasks really well, or at least that's the goal. So we kind of make it, make the neural network predict the correct example from a bunch of examples which contain mostly negative samples and one positive example. So you can think of it as taking, if you have a continuous audio waveform, think of sampling a bunch of audio downstream, let's say from the audio where you're using as the context. These could be audio samples from the same audio, or it could even be audio samples from some other audio not directly related to this audio. And then Those are all the samples that exist here that you actually take them through the encoder and then get these latent space representations. Same thing with C, this encoder and this encoder are exactly the same. And you then try to use, or by using this loss, you train it so that it's able to do a good job of classifying the positive example and not classify correctly, if you will, or say that these negative examples, that the other latents are negative examples. And so there is a ground truth that we know because we know already what is the correct sample. This is all known. We have the full audio waveform, and then we just take chunks of it, put it through the encoder, take the context chunk, and do what I just talked about. So this is, as you can see, very similar to what is done in Word2Vec. And then if you do the softmax and you have a scoring function, then you can use any number of scoring functions, but the scoring function is just assigning some score between the embeddings, or assigning a score to the embeddings, so that the correct score between the context and the correctly predicted or the positive example is good, whereas the distance or the score between the context and all the negative examples is, quote, bad score with respect to the score, and the positive example has good results with respect to the score. And the one thing which I didn't look into in great detail, so the scoring that is used, they say in this case, is instead of a regular dot product, is a bilinear dot product. If anybody is familiar with the math behind, how exactly is a bilinear dot product calculated, I'd be all ears. I didn't have the time to kind of get into the details of the bilinear dot product calculation, but it seems what is mentioned in the lecture is one of the advantages of using a bilinear dot product seems to be that you don't have to normalize, whereas obviously for amplitude reasons, you typically normalize the dot product if you're just taking a linear dot product. Anybody familiar with what the bilinear dot product is or why it is done other than what is stated of, oh, you don't have to normalize? No? Okay, so that's a detail that I wasn't quite clear on. There are some explanations on the web of what is a bilinear dot product, but that's not what I'm interested in. What I'm interested in is why, maybe it's explained in the paper. Again, I haven't gone into the details of reading up the paper, but that's just some detail that at least I'm not totally familiar with. So in other words, this matrix WK now, it begins to learn something, some kind of an association, if you will, some property that helps us kind of correlate different things. So it helps correlate the context in the latent space from the correct prediction, if you will. So that's kind of what is going on in the CPC effort. So we take, as is shown here, a bunch of audio samples, chunk them, take them through the encoder, take them through autoregressive model. Interestingly, at least in the lecture, he talks about this could just be a GRU it takes it to a number of chunks, and then in the latent space, use the context to, and this is important, do a prediction of multiple future chunks at multiple future time steps. So remember that if it's CT, then you try to predict, and you just don't try to predict at future time, say t+1, but you try it at multiple, or you predict the latents at multiple time intervals. Right? So encode each chunk with a shared encoder, and this can just be a strided convolutional neural network, and then this can be a GRU, take that, find the latents, and do this kind of final hidden state or the context state to do excuse me, future latents of the true audio chunk, and you do that by training with the correct future and a bunch of negative futures or fake futures, and try to maximize the embedding so that the correct future is very correlated with the context and all the negatives are far away. Now, what you could do is sample the positive. Obviously, we want the correct positive, but then for the negatives, you could use the negative from the same audio signal, or you could use the negatives from various different audio signals. And this choice becomes very important in this whole contrastive predictive coding. So what do I mean by this choice? The choice of the negatives that we use is very important, because depending on the choice, the encoder ends up learning different things. So for example, the example they talk about in audio, because it's conceptually easy to understand, is let's say we take the audio signal of speaker A saying certain things, of me speaking and saying certain things. Then you could conceivably, in the negative examples, take a bunch of audio signals of different speakers saying the same sentence or the same set of words. If that is done, then the encoder ends up learning one set of embeddings. If, on the other hand, you take an audio signal of somebody saying particular set of words, and then use this different audio signal of the same speaker saying a different set of words, then the embedding learns here are different, and they end up learning different things with respect to what it learned when different audio signals from different speakers were used. So in one case, if we were to try to predict the speaker, let's say we have 10 speakers, and we have taken audio signals from each of the 10 different speakers as the negative examples, and we try to train the encoder using that. So it predicts the correct positive example of the correct speaker versus the 9 negative examples of the wrong speakers. Then the encoding that it learns is able to maximally predict the speaker. If, on the other hand, we choose negative examples of the same speaker speaking different set of words, then what the encoding learns is kind of the phonemes that the speaker speaks. So you can think of it conceptually as the accent of the speaker. So in one case, it learns the quote identity of the speaker, meaning in the sense that it says, oh, these embeddings are not the same speaker. If you have a choice of 10 speakers, it is able to correctly predict the embeddings in the latent space of the same speaker versus all the other speakers. In this, if we use the choice of using the future embeddings, but of a different set of words of the same speaker, then it ends up learning the accent or other things in the sound that are different when the words change, right? So in that sense, the choice of the negatives provided to the contrast in the contrastive predictive encoding becomes important. Now, one other thing which is kind of interesting in this case is there's no reason why, even though I use the word future and past and so on and so forth, there's no reason why it ought to only go from the past to the future. You can conceptually set it up to have words from the future predict the past. And you can also set it up such that there's a window in the middle that you're trying to predict, which is what you can think of the continuous bag of words in Word2Vec does, which is take a window from the past and the future and kind of predict what is in the middle. So there's no inherent reason why this couldn't be done in, even though I use the words, past to predict the future, there's no reason why it can't go in the other direction and so on. So the interesting thing is that the context and the targets that are chosen become important in this case. As I just explained, the negative choice is very important to what the embeddings end up learning, right? So conceptually, you can think of this as, and we looked at a bunch of different methods in the previous lecture of jigsaw puzzle, rotation, things of this nature. So you can think of contrastive predictive coding as kind of providing a framework in which a variety of these kinds of things are being tried at the same time. So it's a generalized approach instead of a particular task like solving the jigsaw puzzle or predicting the rotation of an image and so on and so forth. So, and this is important. Why? Because it's also important to understand that this is where the fact that contrastive predictive encoding doesn't just predict one time step latence, but it attempts to predict multiple time step latence. And we'll also look at interesting things with respect to that choice here in a minute. But so the point here is that it's a multi-step prediction task. So if we look at multiple predictions in the latent space that are then emerging out of the context prediction, right, then you can think of different W matrices being learned. So that's kind of what is shown here, that you do predictions not just at this single future latent, but at multiple time steps, and which in turn, where K is kind of the time steps. And so you end up learning multitude of the WKs that help you predict multiple time step futures, right? And each of these, you can think of it as predicting one step ahead, two steps ahead, three steps ahead, four steps ahead, and so on and so forth. And the contrastive predicting infrastructure that is set up helps us optimize all of these predictions at one time, right? It's kind of, this setup is helping us optimize this predictions, all these predictions simultaneously, right? So we are forcing the representations learned by this encoder to be able to predict these various time steps in one go, in one shot. That is, it has to be able to do well, not just in predicting the first time step, but the first, the second, the third, the fourth, and so on. Right. So that is where this conceptual understanding of contrastive predictive coding as a task which kind of does a whole bunch of pretext tasks, not just a single pretext task like predicting a single angle of rotation that your image has. It's as if contrastive predictive coding is set up to be able to do multiple pretext tasks at once. And by doing them, by forcing it to kind of do multiple tasks at once, the embeddings that it learns are much better. So you can also see this diagram tries to explain kind of conceptually what the network that we have, which is the encoder network followed by the autoregressive model on top of it, what it is actually learning. So in that sense, what it says is, in an audio waveform, down in the lower layers of your network, you have these things which are fast varying. So this is raw audio, high frequency signals. And then as you go further up, or that means as you are going deeper into our network, these are things which are slow varying. So this things in this space, right, these are high frequency signals in the sense that they vary quite often. Whereas, as you keep progressing, you tend to come to the space where the signal is much more semantic. So you can think of what I just said before of predicting the identity of the speaker, which, in some sense is learned in these higher layers, if you will, because it doesn't change from prediction to prediction in a high frequency manner. As you provide negative samples of future targets, and as you realize they are not from the same speaker, that is something you begin to pick up at the higher levels of the network or deeper into the network, not closer to the high frequency changes. Right. So what it's trying to learn through the setup we have of the encoder and then the autoregressive model on top of that is things which are in this domain. By that I mean the things that are of a semantic nature that then helps it to do well in other downstream tasks. Right. So it is the slow varying, high content like the phonemes or the identity of the speaker. So instead of making predictions at this high frequency domain space, it learns the latents to be able to, or it learns the encodings in order to be able to make the prediction in the latent space using kind of the semantic information. So as we keep processing this audio signal, the information becomes more and more semantic, right? Which means it kind of tries to extract the underlying meaning. So in an image, it would be things like a dog, a cat, a car, and things of this nature. In an audio waveform, it could be things like the accent of a speaker, the identity of a speaker, and so on and so forth. So again, much like we saw before, it's important also to choose the targets that are not necessarily overlapping with respect to the context. So not only are the negatives and the type of negatives that we provide for this contrastive learning important, but it's also important to choose the targets at a distance conceptually that is separated from the context, right? So it shouldn't be overlapping with respect to the context. We should choose targets which are reasonably ahead, and we'll kind of get into a discussion in a little bit of what reasonably ahead means, in order to be able to grasp, in order to allow the network to be able to extract the semantic information, right? So the steps that we choose in this setup of T+1, T+2, T+3 need to be far enough from each other that it actually provides a good choice. So it needs to have a gap between the context and the target. So between CT, which is the context, and ZT plus K, which is K is the number of time steps between them, right? Since why is that important? Well, if you're choosing very close to each other, then the network will not be able to extract the semantic information, and secondly, the semantic information would not even have changed, because the changes in the semantic information happen when, in some sense, the gap is more between the context and the target. And again, you can think of it as, the more it in terms of phonemes and stuff, the words have to be sufficiently different for the speaker to speak different words with a different accent and so on in order for the accents to be learned. Or if you think of it as identity of the speaker, then you need to have enough examples of the negatives of the identity of different speakers with respect to the current speaker in order to be again able for the network to pick that up. So that's why the distance for the choices of the targets and the distances at which they are with respect to the context becomes important in order for the embeddings to become rich enough to be able to tell the difference. So what we've kind of seen is the negative choices are important. The sampling of the negatives and the targets, the space, quote unquote, or the distance between the targets and the context are important. And provided we get those two things right, then this kind of a setup of contrastive predictive encoding, what they show in the paper is it does a really good job of being able, for example, to pick out the quote correct speaker with respect to non-correct speakers or stated differently, it's able to identify or it's able to classify the identities of speakers really well. And you take the embeddings and you kind of do a t-SNE projection down to 2 dimensions, and you can see this nice separation of the identities of different speakers using the CPC framework on the left. So that's what this t-SNE plot shows, and you can see that they're kind of nicely separated in the high embedding space, the embeddings that are learned, and the embeddings are used to then predict the identity of the speakers. Now, the interesting thing, this is with respect to the identity. Now, on the right, the choice of the time frame or the time steps that we use is what is shown. So this is the average accuracy of predicting the positive sample in the future. And as you see, as we increase the distance between the context and the prediction or the targets, the accuracy of prediction goes down, right? So the model predicts up to 200 milliseconds. Every step consists of 10 milliseconds. But what is interesting is the accuracy drops quite a bit. So this table kind of compares the CPC approach with for 2 tasks. One is the speaker classification task that I talked about, which is identify the correct speaker. The other, what it says, phone classification, is a phoneme classification, and it does the comparison of accuracy of the different methods here. And then we'll look at the right table next. But staring at the accuracy table, what you can see is the CPC method gets you very close to the supervised technique. And the MSCC features apparently are hand-coded features. So compared even to a hand-coded approach to solving the ability to predict identities of speakers from the audio signals, you begin to learn why the CPC method of saying, hey, I want to kind of push the embeddings of the positive examples closer and the negative examples far apart. That kind of a simple setup gets you very close to what supervised learning is able to do with respect to speaker classification. With respect to phonemes, it doesn't do as well. There's still a gap of about 10 points in accuracy, but it is by far the best of the methods when compared. So here the gap is significant. Here the gap is not that much, but in both cases, when you compare this to the 2 techniques in this case, they are worlds apart. Now, if you take the right table and you look at the negative samples, and you take the negative samples from the same speaker, then you get the accuracy of about 65.5. And instead you take the negative examples. On the other hand, you take the negative examples from the mixed speaker, you actually see the score drop a little bit. So in this kind of an evaluation, it tells you that it's able, if the same speaker is there, then it's able to do it a better job than if you mix up the speakers. Right. And one thing I forgot to mention is the way you determine the accuracy is you take the encodings that you get from the contrastive predictive setup, CPC setup, and then freeze those encodings and put a linear classifier on top, and then perform classification tasks. Okay, and how do you classify? You classify for phonemes. You say, I want you to tell me one of 41 possible classes as the positive class, and 40 of the 41 are therefore the negative classes. And when it comes to speaker classification, you do the classification of one of 251. So that's what accuracy means. So accuracy means putting or being able to predict the correct identity of one of 251 speakers, and in case of speaker classification, and in case of phoneme classification, it's the same speaker, but you need to be able to identify the phonemes of one of 41 possible classes. So that's kind of what you do, and that's how you score the accuracy, right? So, and now the this is all done using just a linear layer on top of the encodings. So this gap that I talked about of 64.6 versus 74.6 is assuming that you put a linear layer. What he says in the lecture is, if you put an MLP, a full MLP on top, which has the nonlinearity and all of that, then apparently, even in case of phoneme classification, you can get, it seems, pretty close to the 74.6 that you see in supervised. So while the phonemes may not be linearly separable, which it seems the speakers are, but the phonemes aren't. But if you put an MLP, apparently with just even CPC, you're getting close to the 74.6. Now, what this right table shows is, depending on where you take the negative samples from, the accuracy score varies quite a bit. And the way to read this, by the way, it took me a little of time to understand that you should think of these as up to so many steps, not just exactly 2 steps, but up to 2 steps, up to 4 steps, up to 8 steps. So when it says 8 steps, what you're actually doing is predicting 1, 2, 3, 4, 5, 6, 7, 8. So you're predicting all the steps up to 8 steps, and so on down this. Because remember that what I talked about, it's the fact that you're doing these multiple predictions at the same time simultaneously is what contrastive predictive coding brings into the equation and helps the embeddings get much better, right? So it is, if you look at this, it means up to 2 steps, you're only getting 28.5, up to 4, it increases, up to 8, increases still further, up to 12, it increases even more slightly, but you can see the increase dropping as we go up. And then when you go from 12 steps to 16 steps, it actually reduces. And conceptually, you can understand this, because what it means is, as long as and we talked about this concept of mutual information. So it seems the explanation of why this tendency happens, or what you see in these numbers, the trend, is because as long as the mutual information between your context and all these steps continues to exist, and you're able to extract that in your encodings, the accuracy continues to improve. But when you go too far out to where there's no longer any mutual information present between the time steps, let's say in the 16th time step in audio waveforms compared to 12 times up to, compared to the case where you predict up to 12 time steps, then you begin to see a reduction in how good your embeddings are when you stick the classifier on top and try to make the prediction. Right. So that's kind of what this top chart shows. And what the bottom chart shows, he didn't get into all the different details here. So what it seems to show is that, when you're doing the phoneme task, then it's, if you use the same speaker, it's able to learn better than if you use multiple speakers in order to learn the phoneme task. So what this seems to then also indicate is the fact that if you are already aware of the downstream task, so for example, if you know that the downstream task is identifying speakers, then you can do one set of things with respect to the contrastive predictive coding infrastructure, which will help the embeddings that are learned be better. If you have the phoneme prediction task, then using the same speaker helps. So in some sense, what you do in the contrastive predictive coding, the negative samples, the distance, those kinds of things seem to vary depending on the downstream task, or or stated differently, if you know the downstream task, you can get better embeddings. Right. So that's kind of what this seems to say. That is, in a choice of negative samples, we can be smarter if we know the task that we are expected to do with the embedding. Right. And it's also interesting, as I said, that if the number of steps ahead that you try to predict is helpful in deciding whether the embeddings that are learned are good, or they can get better, or they get worse. So the right way to think about it is that the futures that we select to predict should be such that they share some information with the context, because that's what allows us, in a way, to learn the embeddings that are valuable. And as we go further into the future, the entropy is higher, the amount of bits that are shared between the context and the target gets lower, and therefore you see this drop between the 12 predicting up to 12 steps and predicting beyond that, say predicting up to 16 steps. So when we do this, then the neural network kind of begins to encode noise as opposed to encoding mutual information, and that doesn't lead to improved accuracy. Right. So any questions? What we've gone through so far? Okay, so this is all explanation in the audio space, but it's kind of one of the spaces that it's very easy to understand the conceptual application of CPC. Now we move to kind of the image space. And again, keep in mind that the goal of the CPC approach or the paper was, hey, can we set up a framework in order that the same framework can be used to successfully self-supervised learn embeddings which do a good job of learning the relevant things in order to be able to perform well on downstream tasks. Now, I want to take this setup and I want to do the task of being good at downstream tasks and learning good embeddings, self-supervised manner, not just in audio, but also in image. So we'll quickly look at what are all the things that are done that we have to now do in order to apply the same framework to images. So that's what all this, the next several discussions are about that. So in case of image, what they have done in order to use the CPC framework is take, let's say, a 256 by 256 image, chunk it. So you have, you chunk it into some, remember we've discussed this now in an audio context, there needs to be some mutual information. So what it's done is take 64 pixel slice, and you take the next slice to have an overlap. So you can think of this as being 32 pixels wide and this as being 32 pixels. So if you do all the math and I work through it, then you'll find that you get a 7 by 7. So this is 7 and this will be 7, 2. So that's how you get these chunks. So you can think of this as kind of striping or gridding the 256 by 256 image, if you will. Right, and then you get a 7 by 7 grid, and you encode each of these patches with a ResNet, and it could be, ResNet 50, ResNet 101, so on and so forth. And by doing that, you get an embedding for each of the patches, right? And so you'll have a grid of embeddings, and you perform based on a context, choose one of these embeddings as the context, and then you predict a bunch of embeddings for the image that's below. for a number of positions, right? So you perform 2D predictive tasks on top of the grid. So treat the grid as your sequence of audio signals, if you will, and then predict the future, right? And the prediction of the future, you can think of an autoregressive model such as pixel CNN and so on and so forth, right? So a bunch of overlapping patches in 2D patch grid, and the task then becomes one of predicting the row of patches that you have not yet seen, right? So you use the first 3 rows to predict the next 3 rows and so on. And obviously you try to predict every single patch in each of the remaining rows, right? So that's kind of the how you translate the CPC task and the CPC framework into an image in a 2D dimension. So now, obviously we'll need to aggregate the context patches, and one of the ways that we can aggregate and summarize what these embedding mean in a spatial location, blah, 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 is all nicely done in what we have already seen in pixel CNN kind of approach. So the autoregressive model that is stuck on top of the ResNet that you learned in order to get it to the latent phase is a pixel CNN model, right? And so you use mask convolution, pixel CNN style models. And in fact, this is where it's interesting because the pixel CNN author is the same first author on the CPC paper, right? And the next slides kind of just show you how it is done. So you can think of an image for a dog and you generate all these overlapping chunks that I talked about, which have some overlap of the images. And then you do what I talked about, which is you stick an autoregressive encoder on it. And then after you've gone through a whole bunch of the other thing, again, in this example of the image as well, what you do is you take a bunch of these patches, which are the wrong patches, that is the negative patch, if you will, and use one correct patch. And the goal of the network in CPC is to be able to learn to predict the correct patch among a lot of negative patches. So by doing that repeatedly and using the contrastive loss, which is the loss of the positive patch should be low, if you will, with respect to all the negative patches. By doing that over and over, you learn embeddings in your contrastive framework of the encoder. You freeze those encodings, take it out, then use that as if it's a ResNet that, in fact, it is a ResNet, but you freeze the weights of the ResNet that you have learned doing this task and stick a linear layer on top and do the predictions. This is what then you get as the results of the top one accuracy when applied to ImageNet. And what you find is for many of the tasks that we discussed in the previous lecture, including, for example, remember we talked about, there isn't RotNet that's mentioned here, but he mentions in the class that even RotNet is in this kind of a ballpark. But there is Jigsaw, there's colorization, there's the BiGAN, things of this nature that we have looked at in the previous lecture. They all learn encodings which only give us about these numbers in terms of top one accuracy on ImageNet. And using, of course, these are using AlexNet as the backbone and the Con5 layer of AlexNet, which is then used, taken out from the embeddings and used. Now, let's say if we switch that to ResNet v2 and we do the same thing, then at the time the CPC paper was published, this was kind of a pretty good result. You get a top one accuracy of 48.7 and a top 5 accuracy of an ImageNet. Remember, we are putting a classifier on top of this ResNet v2 trained using the CPC framework. where we chunk all these images, predict all the different chunks using pixel CNN on top of the embeddings, and then take out the embeddings from the, or take out the ResNet, freeze the embeddings, stick a linear layer on top, stick a classified layer on top, and then this is where we end up. Okay. And so that's kind of what this setup of chunking and then predicting and learning the embeddings gets us to, right? 48.7 and 73.6, much better than any of the other techniques that we have seen so far. Right, and you can see that there's a significant jump with respect to CPC compared to even Jigsaw and colorization, which by, at least at that time, were kind of state of the art with respect to what was being learned in self-supervised learning. Right, and they try to also apparently in the paper say what is learned in the embeddings when we go through this, and what you see is that different image patches that activate a particular neuron in the CPC architecture. So you see that there are semantic things which are learned, such as, you know, eyes of faces and keyboard-like things and wheels of cars and faces of dogs and things of this nature, which is, you know, to say that a lot of semantic information is picked up by this self-supervised task in embedding. So that is, it is capturing many of the high-level image features and not the low level or high-frequency features, not just you know, the nature of lines, diagonal, vertical, circle, things of that nature, but conceptual categories, if you will, or semantic encoding or encoding of semantic concepts. Right, and then they didn't discuss in as much detail as audio and image the next two fields in which CPC is applied, one in natural language. And you can again see from a benchmark perspective comparing, and these are, you know, different metrics of comparison. These are the different methods that they compare against. And you can see that CPC does not necessarily the best, because in some cases, as you can see here, there are better methods, but it holds up and it is in the ballpark, some cases the best, in several cases not, but it's in the ballpark of some of the other techniques that help. So it's good from the standpoint that it is this particular framework of CPC. Now we have seen it applied to audio, we have seen it applied to images. While it is not the best in NLP, it's also reasonably among the good techniques for text as well. And then the same is applied to reinforcement learning. And what he says, and we have a full lecture dedicated to reinforcement learning and the whole self-supervised learning and so on. The thing to take away, at least from this lecture, is to say that in reinforcement learning, when it is applied, when CPC is applied, the way to think of it is to say, how does it help? Well, it helps in accelerating the learning. That is, in saying that we need to use a lot less data examples for the correct policy to be learned, if you will. So it's the fact that this technique, CPC technique, helps us become more data efficient when it comes to RL. So the model or the agent learns faster the correct policy than it would have if we didn't use this technique. So in parallel to just optimizing for rewards, you also use this technique, and this technique helps to reduce, I can think of it therefore as auxiliary losses to the loss that used for rewards. And the auxiliary laws help to accelerate the learning, meaning that you use less examples and you learn faster. Your model learns faster of what the right policy to follow is. Okay, so this discussion so far, what we have learned are the basic concepts of CPC, right, which is contrastive loss, that is a loss comparing the positive to a bunch of negatives, then the correct choice of distance between the context and the future in predictions, because that helps us learn good embeddings, and the correct choice of negatives, right? So those are the things that are important in a contrastive loss kind of framework, and these are some of the underlying principles that we use in contrastive loss. And those are the basic things introduced and explained and benchmarked in the CPC1 paper. But you can see that the numbers that are achieved, for example, in image classification, is about top one accuracy we saw is only 48.7. Now, when you compare it to supervised learning, the supervised learning is in approximately 76% top one accuracy on ImageNet. So when you then look at a 48.7 number, the gap between this guy and this guy is vast. So it's not the case that supervised learning can claim that it's anywhere close. Self-supervised learning can claim that it's anywhere close to supervised learning. And remember that we set out to kind of say, hey, can we get supervised learning? Can we get self-supervised or semi-supervised learning anywhere close to what supervised learning gives us? So obviously, that was not accomplished by the CPCV1 paper. So in CPCV2 paper, which one of the co-authors, as I said, is this guy Arvind Srinivas, who is the instructor for this particular segment of the course, is one of the co-authors on the CPC version 2 paper. And the goal of this paper apparently was just to attempt to bridge the gap between supervised learning numbers and self-supervised learning numbers, right? And as he says, most of the changes in CPCV2 are hacks, or essentially every attempt at engineering the process to get to the numbers that we are seeking, right? So various parameters that are used in CPCV1, they tried all kinds of different techniques, basically engineering the approach to get to the goal, right? So that's kind of the methodology or what they did in order to get the numbers that you'll see CPCV2 achieve. Let's see. So what they did in case of CPCV2 is they use a much larger ResNet. So we so far had been using ResNet 50, ResNet 100 maybe, but they used a ResNet 161 as compared to the V2. Also, they use 2x the width, which means the number of channels. Always confusing to me. Width is used in many instances to indicate the number of channels. The width is increased, and you end up with about 4,000 features at the end of this ResNet. And then you get the embeddings for every single one of these patches, and you process it with pixel CNN. And again, you increase the width of the pixel CNN to be 2x wider than the pixel CNN used in version 1. And the one other modification, not just one other, but among the other modifications they did was, remember we talked about this importance of finding the correct future to predict, because if you predict too far into the future, or I should say up to the correct future to predict. So if you predict too far into the future, the 16 steps versus the 12-step comparison in audio. So that's important. So in this case, what they figured out was that if you predict with only one offset, remember that in the image case in V1 CPC, they used the top 3 rows to predict the bottom 3 rows of this chunked image. In this case, they didn't do that. They said, oh, we learn better embedding if we use the pixel CNN to just predict a constant distance down from where we are. So it only predicts 2 rows down. And actually we'll see in a minute they play some other games as well. So doing a lot of these ablations, they figured out the various engineering knobs to set in the correct way in order to begin to bridge the gap, right? So so that's the information overlap kind of concept that, if you pick the right distance with respect to the target, that helps you get the best embeddings, right? So for the kind of overlap in the image that they applied, they figured out that predicting 2 rows down and just 2 rows down was the best way to go for the model, right? And they kind of do all this and figured out, yeah, obviously this loss continues to be the contrastive loss, and predict just 2 rows down. And the negatives, as I keep repeating, are other patches within the image, or you could use patches from other images, right? You could use patches from other images, and that's a version of this network called AllNet that they use. And let's see, they used any other technique. Oh, that was it. The one key concept again to learn is this whole contrastive loss and setup is apparently referred to, and you'll see this used in more and more papers. So it's useful to know this is apparently referred to as info NC loss. I think this is noise contrastive estimation. So info noise contrastive estimation, or info NC loss, is what is used in CPC version 1, version 2, and in many other papers they try to do this kind of learning of using the correct future versus the lots of negative futures, and learning the embedding from that, and trying to get the associations. Now, the good thing, as we've seen, is this is obviously a lot of stuff can be done in parallel, because the parallel implementation of the pixel CNN, and then eventually you'll see that this thing change. But right now we just flatten it. That is, we reduce the width eventually by just using a 1-by-1 convolution and getting it to the 4000 flat vector that I talked about. Right. And they increased, the other tricks they pulled were to increase for every single one of these patches the number of augmentations they did, and that is taken to an extreme when compared to CPCV1. That in turn, what it means is it increases the number of negatives, right? So that's another way in which CPCV2 is made to be better than CPCV1. Now here, in fact, thanks to Arto, I kind of listened to, I haven't finished listening to it, but it's kind of interesting, the stuff that he mentioned last week, the podcast. And what is in the podcast, there's one thing which is mentioned, which the class doesn't highlight, but it's an important, I think, for us to grasp, which I didn't know until I listened to the podcast, was the type of augmentations that are used in self-supervised learning is different from the augmentation that you would use for supervised learning. And it's kind of interesting or fascinating to think about why that is. And that tells you something about, at least to me, it was interesting to think about why that would be the case. Anybody know the answer or want to guess an answer of why the type of augmentations we perform for self-supervised learning would be different, let's say for CPC. And I just mentioned that, that they increase dramatically the augmentations for CPCV2 versus CPCV1. But in general, the question is, why would the augmentations you apply for self-supervised learning be different from the augmentation you apply in supervised learning? And
well, I don't have like an answer, but well, as I understood it, first those self-supervised approaches that this guy Misra talking about, they are kind of different in terms they don't use this style of pixel CNN model. It's rather contrasting the encodings of the same picture, heavily augmented by the same or very similar networks. So that's a bit like different from what we have here. And what is kind of argued in this self-supervised learning like discussions currently, I believe in image domain, I believe. So the idea is that basically this augmentations that are done to the images are the place where we kind of shift our prior knowledge that we have of the domain. So essentially, it might be thought of as selecting these augmentations is kind of a way to transfer the information we are expecting to be useful for the model to help the model learn. So in a sense, we are like, or not we, but the researchers working on the self-supervised learning, they are like to select the augmentations which will be most useful for a network to learn useful features. And basically, for now, this kind of choice of augmentations is driven by kind of human intuition and is heavily empirical. So it's not like we probably will have this concrete answer right away. And also, I believe in that same podcast you mentioned, it's also discussed that maybe one of the possible next steps in advancing the self-supervised learning would be getting rid of these heavy augmentations and finding some other way to make the neural networks learn useful representations. Because like with these neural networks, what we probably want is to avoid introducing any prior knowledge to let the networks discover what is really underlying data distribution without kind of biasing these networks by our human experience on one hand, but on the other hand, this kind of contradicts the current practical interests. So in terms of data efficiency and so on. So that's my just some points on the question.
Yeah,
but
no, I think you captured it right, which is, and especially when thought of it in the context of in case of supervised learning, for example, if you're trying to learn the ImageNet classes, then what you want to do by, say, horizontal flipping or rotation or things like that, you're kind of telling the network that learn the underlying classes invariant to these things that I'm changing on you. So a bicycle is a bicycle, whether it's lying horizontal on the floor or it's standing vertical. A dog is a dog, whether it's looking at the left or looking at the right. Things like that. I mean, I'm oversimplifying, but kind of conceptually like that. But when it comes to self-supervised learning, then what you don't want the network, and this is precisely what you worded there, which is to say you provide human intuition through augmentations that help the network pick up the correct embeddings. That's the key thing. So the reason is, so now when you think of it that way, so this is where the podcast helps, because he's saying that in the podcast, in a couple of different podcasts, because the Simpler guy who wrote the Simpler paper, which we'll discuss in a few minutes, is also interviewed in a different podcast. And he says something fascinating too, which is you can think of the this contrast negative learning, which is the setup we have for CPC and stuff, or or supervised learning, as kind of cheating on an exam, because you're given the right answer, given the right answer, given the right answer, and so on. Now, when you do this contrastive thing, right, then the network tries to cheat to figure out the easiest contrast between the positives and all the negatives. So for example, if you have a dog and most dogs have a particular color, the network will just stick on the color and say, if it is color X, I predict dog, right? And you don't want that to happen, because then the network is not learning the rich representations that you're after. Therefore, and this is what you mentioned, Ato, which is therefore the human intuition comes into play to say, oh, I don't want you to learn that. I want you to learn more complex things about the dog than just the color and predict based on that. Therefore, I throw in an augmentation where I remove the color from the dog image, for example, and force you to learn the dog class. And that therefore says that the type of augmentations, like removing color from a picture, are important for self-supervised learning, but not so much for supervised learning. As an example, so there is a distinction between the type of augmentation you throw in for, and I thought that was fascinating because it captures what you said, Ato, which is that ultimately the goal is to try to help the network learn, but learn what and how it does its job and what makes it learn the richer set of embeddings versus taking a shortcut and figuring it out, are kind of fascinating twists to what type of augmentations you provide for the different tasks. And it's the same Ishan Mishra, by the way, I'll also post in the NYU lectures, he talks somewhat about this with respect to the PIRL, which we don't get into in this class, but it's yet another technique that's used for self-supervised learning. So I just thought it was a little bit of a detail that is generically applicable. That is, in terms of augmentation, we should always be thinking of it as helping the network learn the right things, but at the same time, preventing it from cheating, if you will, in order to kind of shortcut the process and learn something that it still helps to achieve the goal, but that's not what we want it to learn, if you will. And that's why what Arto said is important too, that ultimately the humans are still providing the background knowledge for that. And if we really want these things to be independent, then, future research needs to be done to get rid of having to have humans provide the list of augmentations that are smart with respect to the task.
Yeah, and just a bit more about that, and that was mentioned in the podcast. So we human basically have all these augmentations naturally in when we learning to see, right? Because we see things in different angles and with a wide variety of contexts, and that's kind of property of our natural environment. And that's why I think that it's really fascinating that this stuff is coming to the is combined with the reinforcement learning framework, and maybe there is a lot of potential to both improve the results of reinforcement learning by having this self-supervised objective added to the task. And also maybe we will discover more about self-supervised learning, because as reinforcement learning agents are kind of interacting with the environment, and there is a way to get this different views of things, and like this difference between important and unimportant transformations will occur naturally. But like now, I guess it's also the researchers are trying to balance the task to be difficult enough, but also useful for networks to learn, as you kind of alluded.
Yeah, agree. So I just thought that detail is a little bit fascinating. As you said, we tend to pick up the fact that an object sideways is the same object, but that's not inherently somehow obvious to networks that have to learn that fact. But growing up, or as we interact with the human, as we as humans interact, that's obvious to us, but that's not obvious. So this whole thing of how to encode common sense is, in even the reinforcement learning world, is like a fascinating problem. Okay, so moving on, since we may run out of time. So contrastive predicting, train on unlabeled, they increased the training tremendously. They trained for a week. Good luck unless you're working on DeepMind. Augment every patch. And this is where the list of spatial and color augmentation. That's where the color augmentation comes in, what we just spent time discussing. Spatial augmentation, again, it's the fact that, if you see a bird in one portion of the image, this as opposed to in a different orientation, in a different part. So it's important to do a lot of it. Then effective number of negatives, increase the large number of negatives. So here, the other thing they do is use larger patches from larger images. So think of it as making everything bigger and then throw in a bunch of critical, more augmentation, more training, increasing number of size of the pixel chunk, size of the image, and all of that. When done, then we'll and then kind of view of the pipeline. Basic pipeline of self-supervised is 100% of the images and 0% labels, right? There are no labels in self-supervised training. We start with 256x253, use a 161 network, and then go through it, mask ConNet on top, and then use the info NC loss that I talked about. And this is the whole pre-training task. Then they do a bunch of things with it, which are fascinating as we look at the results. The first thing they do is take out the embeddings and obviously do the linear classification and using a cross entropy and try to predict the correct class. Then there's something else they do, which is, let's say, and this is kind of, there's a whole lecture dedicated to this in the future, which is semi-supervised learning, which is if instead of saying 0% label, what if we then provide some small fraction of the labels and fine-tune the network, right? So does that help us get to better results? So the point here being, once we are pre-trained by using no labels at all, how much faster can we learn if we have a very small proportion? Because this is very useful in cases like medical imaging and stuff where the number of images are very low. But if you're successfully pre-trained in a self-supervised manner, how good or how much faster using these self-supervised embeddings can you learn if you only have, let's say, a fraction of the labels as compared to 100% of the labels, and we'll see the result of that. And then transfer learning, which is take this network, the ResNet 161 that we have learned, and apply it to a completely different task, not just this classification task, but for example, an object detection task, right? Which is the thing on Pascal POC. And obviously compare it to supervised learning, which is our basic reference comparison. So these are all the different things that they did in CPCV2 paper, and you begin to see the results. And right, and we kind of begin to see how it does. Remember, CPCV1 was 48.7%. That's the number here. And here are some of the other comparisons. And what we find, and also we begin to see the paper we'll discuss in a little bit, the momentum contrast paper, which is about 68.6. They achieve 71.5 with CPCV2 with a ResNet 161 model. Keep in mind, this is getting very close to the 76% of supervised classification, right? That's kind of what the goal was, to get it to 76. And, you know, in terms of if you take a basic, obviously ResNet 50, then you get about 63.8. And obviously the parameters that are there are significantly different. It's only 24 million parameters. You still get a reasonably good number, and compared to the momentum contrast, it's much better as well, right? So the point is, by doing a bunch of engineering stuff, increasing augmentation, increasing the network, increasing size of image, increasing the overlap, playing different games with the augmentation tasks, and so on and so forth, and then you know, you get really kind of state-of-the-art results at the time. And he says it was published fairly recently, which meant spring of 2 years back, 2020 spring. Now, here's the other interesting or fascinating part that I think is relevant to people working in other domains like medical images and so on and so forth. So this red line is a line of supervised training, so ResNet trained on pixels, whereas you can think of the blue lines as the CPCV2. Now, you can think of along the x-axis is the percentage of label data. So what this tells you is, let's say this domain, and I'm going to kind of make an arbitrary separation, but let's say this is a domain of high label data availability, so high data availability domain. So in that kind of a domain, the point is that if you pick, let's say, an accuracy, right? So this is the top 5 classification accuracy. So if you pick 90, I'm going to roughly squint at it and think this point is at 90. Then what this says is, at 90% accuracy, you can use a significantly lower percentage of data. So, you know, meaning that your data percentage is 10 here, and your data percentage to get to the same accuracy is 20 here. So at 50% lower labels, you're able to get to the same accuracy as what your supervised training provides. And what's fascinating is you see this curve is a lot less flat than the supervised technique curve, which means that in a low data regime domain, which means you have, you know, available labels are very less, then you can achieve the same level of accuracy. Let's say this is 75, again, squint and assume this is 0.75. You can get, and while the curve doesn't, you can kind of think of it as, let's take this point, which, you know, is at 75, then you can get at 1% as compared to, I don't know, this guy being like, say, 6% of the data. So 80% fewer labeled data, you're able to achieve the same accuracy. So that's a significant help, even if you don't achieve the exact same target of best accuracy with self-supervised learning. This graph tells you that you're much better off coming up with these techniques, because using semi-supervised, or at least very small number of labels, you can get to a significant proportion of your accuracy goals that you achieve with fully supervised learning, right? So by training on whatever labels you have, which is a lot less, you can still get very good results, provided you are pre-trained using self-supervised techniques. that's a very important and a key benefit, at least, of the whole self-supervised. And we dedicate a full lecture to it of semi-supervised learning. And that's coming up, I think, next, if not after the next class. Right. Any questions with respect to this? Okay, so interest of time, moving on. This is just a graph which, he talks about, layer norm, and he talks about all the different augmentation, but you can think of it as the ablations which get you from 48.7 in Void 1 to the 71.5 that you see in V2. Okay. Interest of time, I'm kind of going to keep moving through these fast because we have 2 more papers to cover, and then this is the data efficiency point that I've already made, and you see that for, these are the different data regimes, or you can think of the different columns as being at different percentage of data availability. And what you see with this is that in every case, compared to other methods, you see the V2 method give you a much better accuracy at every data slice. And what is fascinating to me, at least, was the fact that even at the 100% data availability, you see the supervised baseline is 95.2. Here you get on, if you fine tune, you get up to 96.5. So this is almost a 1.3% difference. Right. So if you fine tune after learning on unsupervised, you're actually able to even better at 100% labels the results that you get using CPCV2. Right. And then the final thing they point out is, this is kind of one of the big deals about CPCV2 is the transfer learning results. So any of these techniques did not get you there, including momentum contrast, which we'll talk about, but compared to supervised baseline, this is the object detection task, and the faster RCNN trained on the CPCV2 ResNet, that this thing gets you to better results than what you get with supervised. So that, was the big deal for the first time, that you were able to get better results than supervised learning on a transfer task, such as object detection, which had not been the case until this paper came along. Right. Okay, so next, hopefully in the next 25 minutes, we can get through these 2. So I might rush it a little bit. Apologies, but the first thing that the future researchers of that other 2 papers, Sinclair and Moko, that we'll discuss, those are the next 2, is this concept of instant discrimination. Now, the point being that in CPC and stuff, you chunk and deal with chunks and so on and so forth, which is a royal pain. And how you grid the images and then create the negatives and so on and so forth. So instead of all that, the instant discrimination approach is to say, I take an image, I perform an augmentation on it, and we kind of spend some time on what kind of augmentations are useful or attractive or applicable in this instance. And then take a completely different image, and obviously my augmented image or augmentation applied to my image is the same image. So it needs to then, the whole setup needs to be able to say, this is the correct image and this is the wrong image. And you do the noise contrastive info NCE loss, but you do it at the level of an instance, and you know what is correct because you are the guy who has this picture and augments this picture. So you know what augmentation you have done, and you know what is the true and what's the false. True, fake, distinguish using info NCE. And that's what the instant discrimination approach tries to do. So, in other words, try to identify the same instance of an augmented image versus something else entirely different. So 2 papers take this very far. One is called the MOCO, or momentum contrast, and the other is called simple contrastive learning. And we'll discuss the results of these 2 and the techniques in those 2. Again, at a higher level, they don't go into very great detail, so I'll be explaining it in a little bit of an abstractive manner. I think we'll need to read the paper in order to get to all of the details, right? So the way to think of it is to think, if you are familiar with the transformer kind of approach, then that's what begins to kind of get applied here. So why do I say that? Because we start talking in terms of queries and keys. So momentum contrast, what they do is you take a query, which is just X image that you have, and you take it to the encoder, you perform a bunch of augmentations on it now, or actually you perform an augmentation on it, and the keys that are there, one of them is the augmentation of the X. A lot of the others are negatives, and there is quite a bit of discussion that we'll have about, how do we choose the negatives and so on. And we'll discuss what this momentum encoder is or isn't and how helpful it is. Decide somehow to find the correct key corresponding to the query, or the distance between the query and the augmented key coming from the query should be small, and the distance between, or the similarity between the query and all the wrong keys should be far or much wider, and apply a contrastive loss on top of it and get the result. So conceptually, you can kind of see how CPC leads to this kind of an approach. So, right. So if you have image O, you perform one kind of augmentation to get the query, and you perform an augmentation from another augmentation to get the key. You saw the dog images, and you extract the color from the dog, and you may have the key, the query, go through some encoder, and we'll, again, as I say, talk about momentum encoder in a minute, and then apply the contrastive loss on top and use the temperatured softmax. Again, there's some discussion that you can check online of what a temperature does with respect to softmax, but provided you choose the right temperature and you choose to do these augmentations correctly, then we begin to see good results in taking this kind of an approach. So the point here is you encode the query, encode all the keys, and compute the pairwise similarities between the queries and the keys, right? You know the target, you know which target among the keys has the correct augmentation, or is the same augmentation with respect to the query. And so you know the ground truth, and you know all the fake images in the mini batch, right? That you have, which are all these cat-like images, which are not the augmented images from what you have as the baseline, such as the dog. Then the question then becomes, what is this thing called the momentum encoder? And what is that? Why this momentum? The point is that when the encoder encodes the queries, the keys then, in the case of the momentum encoder, the keys become a historically average value of the same query, right? And there seems to be a lot of benefits to using the historically averaged encoder. Because what you want to do eventually is you want a lot of negatives, right? And if in a mini batch of your keys and queries, if all the negatives, and remember this whole method hinges on using a significant number of negatives and putting those negatives at some distance away from the embeddings that you learn with respect to the positives, right? So it's very crucial to have a large number of negatives. Now, if that is the case, then, and if you're using a mini batch, you're kind of constrained to using only one, obviously we want to use one positive, but you're constrained to using only the size of the mini batch if you're using negative from that mini batch. So that means that you are dependent on the size of the mini batch for the quantity of negatives that you can use in the optimization, which then leads to having to use a large number of or a large sized mini batch, which in this approach, they found, I think you'll see later on, that they kind of had to stop at about a size of 1024 because they couldn't fit that more negative images than that in a mini batch with the GPU size, GPU memory size, and so on and so forth, right? Because the whole thing depends, as I keep repeating, on the contrast at the instance level between the negatives and the positives. Now, the encoding idea, basic idea of the momentum contrast thing is, let's use some kind of a dictionary or some kind of external storage to store a bunch of negatives, thereby making the negatives size or quantity of negatives independent of the size of the mini batch, because then we are not restricted to using negatives from the mini batch. But if we do that, then again, remember that the negatives ought to have some, or the positive and the negatives have to have some relation to the thing that you're also trying to encode. There has to be some mutual correlation between the positives as compared or contrasted with the negatives, right? So that becomes an issue as well. And that's the reason why, instead of just storing a memory bank, as you will see if you get into the blogs that discuss this, which is just a store of encoded values of negative images, you begin to use a dictionary which tends to encode momentum slowly into the keys and then use that value instead. Now, in all frankness, I haven't done a great job of explaining the need, or over time, you'll see as you discuss the papers, they eventually conclude that the momentum thing is not all that important. But at least in the paper, when it was originally published in MoCo and stuff, this seemed to be a very key way to step away from the problem of your batch size being a determinant of the quantity of negatives that you can use. Therefore, they went to a memory bank, and then the memory bank didn't, of using all kinds of other negatives, didn't do a good job, and then they compromised by using this momentum encoder kind of approach. And you can kind of look at the details in this algorithm that's explained. Again, apologies, we're running out of time, so I'm going to skip the discussions, but you can see that they take it to the take each of them, the query and the key, through the same identical encoder, do a batch, that's the DNN, multiply, and then they just concatenate the negatives and the positives, and then they do a cross entropy on the logics and back propagate. Now, the interesting thing, again, is in a MoCo kind of context, there are three different approaches. One is end-to-end, in which case you apply the gradients and allow the gradients to propagate through both encoders, which is the queries and the keys, and you use the same encoder for the query and the key. And in this case, as I said, you're limited by the number of samples that you can use in the mini batch in the negatives. You sidestep that by using the memory bank, but when you start using the memory bank, then obviously you are not back propagating. So you put a stop on the back propagation on this path, only back propagate to the query. And then, because of the issues that I discussed with respect to the memory bank, you go to the momentum encoder and you stick with only back propagating through the query, but then you use the momentum encoder to pick the set of queries that you compare with, right? And this is the graph that I was referring to earlier, which talks about, here they stopped with the size of about 1024 in an end-to-end approach. And the end-to-end approach is, identical encoders on both parts, if you will. They stopped at about 1024, but if you use the memory bank and the MoCo, you can see that they scale fairly well with the number of negatives that you use, and the accuracy continues to kind of grow up. About this regime, at some point, it tends to flatten, and MoCo, which is the memory encoder, kind of gives you even better results than memory bank based approach, right? And using these kind of techniques, they were able to kind of, and this 1024 limit is because they were able to only put, the memory for all the negatives. If they used and stuff in a 8 GPU Volta, they were only able to use about 1024 max batch size with the end-to-end approach, right? So The primary difference between MoCo and the SimClear approach is the fact that SimClear basically continued to stick with the end-to-end approach, and then they did some other techniques, but instead of using the momentum encoder, they kind of chose this approach, if you will, the end-to-end approach in the way they did it, and then they just increased and used much larger TPUs and a bunch of other things which help them get much better results. So when MoCo was published, and apparently MoCo was published before CPCV2, they kind of came to a state-of-the-art results with respect to the accuracy, coming very close. As we saw earlier, they were around at 68. Obviously, CPCV2 came in and did better later, and then there was this bouncing back and forth between MoCo and SimClear. So then we discussed the simple framework for contrastive learning of visual representation, and this is the second paper that is key. There have been other papers subsequently to both these which have kind of pushed the state of the art, but because these are foundational, at least in the class, they discuss these two in much more detail. So the key difference, one of the key differences, as I mentioned, is they take the end-to-end approach. So they take X, which is the image, they kind of apply two different augmentations, go through the embeddings to generate the representation. And here is the other key difference. They apply an MLP on top of this learned representation, which is HI and HJ, which MoCo does not do. And then they, in the latent space of ZI and ZJ, they maximize the agreement between the corrects and maximize the disagreement or the negatives, right? So they put an MLP head on top of the representations that you would learn, for example, in a MoCo. And this MLP head was a key differentiator that gave a very significant performance boost to the SimClear approach as well, right? So in effect, you take a ResNet, which is doing all the encoding, and then you stick another MLP on top of the ResNet, the 161 that you've learned, and that's what gets you, among other things, a big boost in your results, right? And this, what it does, it takes the F embeddings and puts it into a lower dimension G space, right? So the innovation, if you will, in SimClear with respect to MoCo is this MLP guy that they use to bring the H's, if you will, to the Z's. So from this to this dimension, there's a dimensionality reduction through the MLP that helps as well. The other thing they do is when MoCo does not, as I mentioned, MoCo does not use the width dimension, that is the number of channels. Eventually you use a 1x1 to collapse the channel. And in this case, they kind of use the MLP to use those channels to map into a lower dimension that helps you get a much better result. So they go from something in this space of about 2K or 2048 to something in this space of about 128 dimensions, right? The other important thing they do is if you're using a query and a key, and a query and the key are just augmentations of each other, there is this question that arises of, oh, if my dog is just an uncolored dog and I'm maximizing these two while, or minimizing, depending on which way the loss is set up, but bottom line, you're kind of maximizing the closeness of the dogs while maximizing the separation of the dog and the cat, then why can't I do it the other way as well, which is to say, I flip the query and the key. Hey, a dog is a dog, whether it's a query or a key. And my colored dog and the uncolored dog become the query in one case, and the colored dog and the uncolored dog become the key in the other case. And I still want to minimize the separation between the dogs while maximizing the separation between the dog and the cat, conceptually. So that's kind of what is done also as an addition to the MLP. That's what is done in this portion of the code. So you kind of say, flip the query and the key, and that shouldn't cause any difference. And that is something they utilize as well. Okay. So the MLP is an innovation. This fact that they flip and do the query and the key thing is an innovation. Obviously, they stick to the end-to-end as compared to the Moco, and they then throw in a large number of training. They add one other significant augmentation, which is a Gaussian blur. And eventually, what they find with a linear classification of using wider networks is simpler, beats, and apparently, significantly for the first time, top one accuracy of supervised learning. So that was the big claim to fame of the simpler paper. Okay, that is the first time that it actually came and beat some techniques in supervised learning that beats the top one accuracy of supervised as compared to unsupervised learning. So that's the big deal. However, you can kind of think of it as benchmark cheating in a way because you're using 2x width and 4x width networks. The question is, hey, wait a minute, that's not what you're comparing with unsupervised. So what if I do the same increase in width in supervised? And that leads to another interesting side note, which I found fascinating as well, that the benefit to increasing the width of the channels as compared to unsupervised learning is much less. So if you compare the slope of this guy to this guy, you can see this is much flatter than here. And you can see the same thing here. This is much flatter than this. So what it seems to represent, again, thinking of it in terms of what the network learns in the embedding, what this seems to suggest is the increasing the width is helping unsupervised ResNet networks a lot more than it does for supervised. And if you think about it, it kind of makes sense in this following way, that the unsupervised network or self-supervised networks are trying to do a much harder task. Therefore, increasing the capacity in terms of increasing the width of the channels provides you a better ability to overcome the channel. Whereas in case of supervised task, it's almost like you're cheating already by giving all the labels. So by increasing your capacity to remember things or to learn the right things, I'm not really increasing your capacity to get the right answer a whole lot better. Whereas here, because you are trying to do a much harder task, the benefit of increasing the channel seems to be much more. Right? So that is, and then the thing, obviously, when these kind of things happen, it is good for the field. The Moco guys came along and said, wait a minute, if you are doing an MLP on top, why don't we throw an MLP on top of our momentum encoder and call it, and increase our training and increase our augmentation, use the Gaussian blur? What the hell does that cause to our results? So then Moco version 2 comes along, kind of, applies their kinds of techniques that the simpler folks used, bigger models and sweep more, use the MLP on top, then their results got a whole lot better as well, right? So that's Moco version 2. And I checked recently, and he doesn't get into it, but as you can well imagine, there's a simpler version 2 as well. So they then adopted some of the Moco techniques and tried to put that into the simpler approach, and that helped the simpler guys get to better results. So Moco version 1 versus Moco version 2, this is where at least the discussion in class ends. Increase the epochs, increase the augmentation, as I said, or add Gaussian blur, use an MLP on top. The one other thing is the simpler guys did this cosine learning rate decay. So throw that into the Moco version 1, increase the number of epochs. So if you keep the number of epochs the same, but you just do discrete cosine learning transform, MLP, and increased augmentation, then you get to, and you look at the results of the ImageNet accuracy, you're already at 67.5, whereas the original MOCO 1 paper was 60.6. If you increase the training from 200 to 800 epochs, you get 71.1, and you see very good results, state-of-the-art results on the transfer task like object detection. And then, MOCO version 2, ImageNet accuracy, here are some benchmarks of longer unsupervised training. But the net discussions that I would say you should take away from all this is the fact that supervised learning, at least today, and it's been 2 years since the course was taught, self-supervised learning or unsupervised learning is very good for two purposes. One is it's almost as good as supervised learning in terms of ImageNet comparisons, if not better, in terms of the learned representations. And secondly, it really is helpful in low data domains because you can do with the semi-supervised learning techniques, which is using a small number of labels to fine-tune after you've done the unsupervised, to really get very good results with very small data. Two other points before we wrap up. We have not touched, towards the end, we kind of completely moved on to images in MOCO 2 Sinclair instead of kind of keeping the broad approach. And that's because there's a dedicated lecture on text or NLP, and there's a dedicated lecture on self-supervised learning and its application in RL, which I think Arto has signed up to teach to us. So those two things are covered in much greater detail with dedicated lectures. So sorry for rushing through the last two papers, but I think in interest of time, I had to do that to wrap up since people have to drop to the next post. One other request, I would kind of urge you folks to sign up for the next part. There are a few more lectures to get through before we are done. So if you see anything that could be of interest to you among upcoming lectures, please sign up on the list. Any questions for those of us who can afford to remain behind and talk about anything on self-supervised learning? Okay, if not, thanks a lot for joining. And I would, if you're interested in this space, the couple of podcasts, and apparently the podcasts also have YouTube channel associated with it. It would probably be even better because you can look at the graphs or other things they're discussing. They seem to be pretty fascinating discussions.
Thank you very much for this session. It was really informative.
Thanks, Arto.
Thank you. Do you have the link for the podcast? I think
yeah, I'll post it.
Okay, great.
Yeah,
thank you.
I'll post it on. Yeah.
Thanks, Srinivas. Great.
Sure thing.